Next, we talk about standard form. Now, trailing zeros in a whole number with no decimal shown are not significant. So, writing 450 indicates that the zero is not significant and there are only two significant figures in this number. When a decimal is shown, the zero becomes significant. So, writing 450 point makes the zero significant. However, placing a decimal at the end of a number is not usually done. Consider this number again, 250,700. According to the rules we've just seen, this number has four significant figures because the trailing zeros are not significant. But if we add a decimal at the end, the zeros become significant. Suppose you want to write this number to 5 significant figures. What will it be? How about 6 or 7 significant figures? You will realize there is usually a lot of ambiguity when we have trailing zeros lying before an understood decimal. To remove this ambiguity, numbers are reported in what we usually call the standard form or scientific notation. Standard method is just a way of expressing very large numbers or very small numbers. Consider this number 32 million. We can write it in expanded form as 32 times 1 million. In fact, this number is similar to 3.2 times 10 million, right? Right. The figure 10 million can be written in exponential form as 10 raised to power 7 or 10 multiplied with itself 7 times. So our number can be written as 3.2 times 10 to power 7. The power of 10, in this case 7, is equal to the number of steps the decimal point moved from 32 million to 3.2. Remember, for this number, there is a non-decimal here. So it moved 1, 2, 3, 4, 5, 6, 7 steps to the left. This is called standard form. The general format for writing numbers in standard form is a times 10 raised to power n, where a is greater or equal to 1 but less than 10. In other words, a can be any number from 1 to 10, but 10 is excluded. N is an integer and is equal to the number of steps the decimal moved. So 5,749,200 written in standard form, the number between 1 and 10 will be 5.7492. The decimal moves 1, 2, 3, 4, 5, 6 steps to the left, so times 10 to power 6. That is for numbers 10 and larger. How about numbers less than 1? Consider this number. Mathematically, this is the same as 32 over 100 million. In fact, this is the same as 3.2 over 10 million. We can write it in expanded form as 3.2 times 1 over 10 million. This part can be simplified to 1 over 10 raised to power 7. If we get the reciprocal of this part, we know the sign of 7 will change to a negative. So our number can be written as 3.2 times 10 raised to power negative 7. This is also standard form. The only difference is that we have a negative power. And the reason is the direction that the decimal has moved. For our first case, the decimal moved 7 steps to the left. The power was positive. In the second case, it moved 7 steps to the right. The power is a negative. When writing numbers in standard form, for numbers 10 and greater, the decimal always moves leftwards and the power is a positive. For numbers less than 1, the decimal moves to the right and the power is a negative. So 0.002541 in standard form. The number between 1 and 10 will be 2.541. The decimal moved 1, 2, 3 steps towards the right, so times 10 raised to power negative 3. It's that simple. We use standard notation to express the submultiples and multiples of the SI units of measurement. Consider this table that we had for the multiples of the meter. Take millimeter for example. It says 1 millimeter is equal to 0.001 meters. We can express 0.001 in standard form. This will be 1.0 times 10 raised to power negative 3. And since this 1.0 doesn't make any difference, we often omit it. So we have times 10 raised to power negative 3 meters. Take kilometer. It says 1 kilometer is equal to 1,000 meters. We can write 1,000 in standard form as 1.0 times 10 raised to power 3. Omitting this 1.0, we have 10 raised to power 3 meters. If we do the same for all the other multiples and submultiples, we have a table like this one.